Okay, now that we've learned how to deal with these right triangles, right, Pythagorean theorem, and how to find anything that's missing, we can talk about applications. So quick review, here's some things that you can use. These are all the tools you have to be able to find different pieces of a right triangle. And so this is all applies only to right triangles. So you've got your Pythagorean theorem, the fact that all the angles add up to 180. Then if you have a missing side and you're given only a side and an angle, then you're going to use SOHCAHTOA and finish solving. If you're missing an angle, meaning you're given only two sides, steps are the same, 1 through 4. But down here at number 5, instead of solving for the variable, you've got to use one of the inverse trig functions, right? The ones with the little -1. What that does is it takes an answer and gives you the angle that was there originally. For example, this one right here, if I want to find this angle right here, and I know that I've got a measurement adjacent to it, and then a measurement of the hypotenuse of 12, let's see, SOHCAHTOA says that's cosine. So cosine of whatever theta is equal to 9 over 12. Now the only way to solve that then for theta, sorry, I gotta clean up my mess there. Cosine of theta equals that. To finish solving, that's where those inverse functions come into play. So it's cosine. We're going to use cosine with the little -1 of, and then 9/12. You can reduce it if you want. It really doesn't matter. It'll give you the same angle. We'll give you that angle theta is about, I got 41.4 degrees. Okay, I found that angle. Now if I want to find the other angle, we can use the fact that the sum of all the angles equal 180. So for this guy, I'm going to take 180 minus the 90, the right triangle, sorry, the right angle, and then minus that 41.4, which is going to give us, let's see, 48.6. Okay, so we've got that guy, we've got this guy, and then we've got one more side to find. And that one, you could use a trig function to solve for it, or since you're given 2 out of the 3 sides, I would just use the Pythagorean theorem. 9 squared plus, I don't know, b squared equals 12 squared. 81 plus b squared equals 144. You should end up with b squared equals, what is that, minus 81? Is that a major meltdown in my head? B squared equals 63. I don't know what that little line came from. Square root. B is the square root of 63, and then when you break that down and stuff, you'll get 3 square root of 7. As long as I did all my math right. Okay, so using those tools, now we can apply it to actual problems. For example, this one shows the Earth, the Moon, and the Sun create a right triangle. Okay, they drew that in for us. The distance from the Earth to the Moon is about 240,000 and 2.5 miles. That's funny. Why'd they put the 0.5? Couldn't they just round it? I mean, that's a huge number, but whatever. So from the Earth to the Moon, so that's this guy right here. This side is 240,002.5. Now you got to be careful and make sure you keep your units consistent. Keep that in mind for when you do the worksheets. Anyways, so it wants to know what the distance is between the sun and the moon, which is this guy right up here. Sun and the moon is that. So I'm looking at my problem. I have this angle, I have the adjacent side, and I have the opposite side. Right? Hypotenuse is this longest thing, which means I'm going to do tangent. Tangent of theta is opposite over adjacent. I've got my theta. So tangent of 89.85 degrees equals opposite x over adjacent 240,002.5. 5. And then to finish solving that, you know that we're going to multiply by that number, 240002.5, so that those cancel. Same thing on this side. So we end up with an answer of x equals 240,000 and 2.5 times the tangent of 89.85, which is about, boop, 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 calculator said, okay, this is what I got right here, 91,673,992.7 miles. Which, I mean, that makes sense. If this part in between here and here is only 240,000, then of course this big long one is going to be a astronomical part. Astronomical. Yeah. Good tie-ins, McCann. All right. Okay, next one says a ladder leans against a brick wall. The foot of the ladder is 6 feet from the wall. The ladder reaches a height of 15 feet on the wall. Find the nearest degree of the angle the ladder makes with the wall. So your pictures are going to be key to these problems. You've got to be able to draw a picture given the information. So here's our ladder. Here's our wall. That's where a 90-degree angle comes from. And then it told you that it is 6 feet from the wall and that the building, or how far it goes up the wall, is 15 degrees, which would be that. So essentially, this is the triangle that you're solving. And you're trying to find theta or x or whatever. That's a right triangle, just in case you couldn't tell. My drawing skills suck. So all we got to do is figure out how to find that angle. Now to find angles, remember, you're going to use the inverse trig functions. So we've got two sides and one angle. We've got an opposite and adjacent. So again, I'm going to use tangent of some angle. I can change it to x so that it matches the picture. Really doesn't matter. Equals opposite, which is 6, over adjacent, 15, which means to find that angle, x is going to be, flip it over to its inverse, 6 over 15. Okay, boop, boop, boop. Calculator says that's about, okay, I got 21.8 degrees for that angle right there. So again, you read these problems. Key is that picture. If you can't get the picture in there, then you're going to get everything messed up. So, or sorry, you're not going to have your triangle labeled well enough for you to be able to set up your things. So make sure you read the problem carefully. Know that it's going to make a right triangle somehow. So you're going to have that square piece there in the corner, right? Your 90-degree angle. And then it's going to talk about heights, which is the up and down. It's going to talk about distances from something, that would be a horizontal. And then anytime it's going, it has a diagonal, then it's actually, or sorry, not always, but sometimes it talks about what's called an angle of elevation and an angle of depression. So here's a good picture of the difference between those. If you're looking, if you have a line of sight, that's this horizontal line right there, right? There's his eyeball, looking through his eyeball, straight out. If this person looks up at something like this plane, this guy right here is called an angle of elevation because your eyes are going from straight horizontal up, like an elevator rising up, getting elevated. That's an angle of elevation. Now the other one is an angle of depression, meaning you're looking out forward and all of a sudden you look down, right? You're depressing, you're going down. That becomes an angle of depression. And it all depends on where that eye is looking the horizontal. So I get a lot of confusion about that, like when somebody's on a building or whatever, and it talks about the angle of depression and the angle of elevation. Well, if there is somebody up here, here's their line of sight, right, there's their eyeballs. If they have an angle of depression, they're looking at the bottom of the next building, say, then this person with the eyes is looking down. Dang it. Here's his eye level, and he's taking his eyes and he's moving them down. This right here becomes that angle of depression. from the line of sight. Not this guy right here. It's from the line of sight down to whatever they're looking at. Now, vice versa, if you had somebody that was down here at the bottom, let's say they're right here, different somebody, here's his line of sight, and he's looking up at the top of the building, then this right here is the angle of elevation because he's looking up to something. So this would be the angle of elevation. And the biggest mistake is that people don't think of the line of sight as the horizontal for it. So the line of sight down to whatever they're looking at is an angle of depression, or their line of sight up to whatever they're looking at is an angle of elevation.